I would like to introduce our next speaker, Steve Ulrich. He's doing a last-minute stand-in for Nandan Shaha. He will be presenting gRIBI gRPC service for RIB injection. Steve is a networking dork at Arista Networks and is coming today to us from Minneapolis. This is Steve's third time presenting at NANOG, and we're ready for you, Steve. Welcome. Thank you.
Yes, I am Steve Ulrich. I'm with Arista. I'm standing in for Nandan Saha, who had something come up at the last minute. All the great stuff in this presentation is Nandan's. Any gaffes are totally me. I'm going to talk about some work we've been doing with some of our customers about RIB injection mechanism here. So gRIBI or gRIBI, the exact naming is something of a bit of dispute, but I'll roll with gRIBI for the moment here. This is a new mechanism for injecting routes into the RIB. So we're going to talk a little bit about the existing approaches for injecting routes into the RIB and how gRIBI addresses some of this. We're going to talk about the gRIBI service itself and then just kind of walk through a simple example of a weighted route injection. So why do this? We have a number of ways to get stuff into the routing table. We have direct programming at low level. I mean, we have P4 runtime, we have OpenFlow. These are very low-level, kind of device-specific and hardware-specific mechanisms for injecting information into the hardware routing table, and more accurately, it's typically into the FIB. We can also do things like, we have our standard routing protocols, but we have BGP SRTE for providing policy. We can inject dynamic next tops with label stacks into things. We can use BGPLU for egress peer engineering. We can also do trick things with things like PCE. We also have, and every vendor has them, at Arista we have EOS SDK, Juniper has Junos Extensibility Toolkit, I'm sure that Cisco has something as well, but device-specific or vendor-specific APIs or SDKs for interacting with the device. And I would be remiss if I didn't point out that there has been some engagement in the IETF around the I2RS working group for injecting routes into the RIB. This never really saw much in terms of traction, but in terms of an open approach to doing RIB injection, some review and some development has been done on this. I'm not aware of any really robust implementations of that at the moment. Now, with respect to the motivations here, direct programming assumes that we have some very detailed visibility into the device's FIB, into the forwarding tables. Maybe we're being very specific about what the encapsulation looks like. It also presumes that the controller has the ability to modify all of the hardware tables. And it's really commonly in these hardware specific programming scenarios that you have to have a detailed knowledge of the topology that you want to resolve to, and so this is pretty complicated. There aren't too many folks doing this out there. I think Open Daylight was probably the most widespread implementation of a controller that supported something along these lines. Using routing protocols, typically involves doing some unnatural acts. We've shoved all sorts of things into BGP over the years in order to be able to do things. If we're doing some surgical route injection, we're kind of abusing ExaBGP and doing something novel on that front. And everybody here, I assume, has done some level of interesting BGP tricks or surgical injection here. But we do lose something when we're doing this. Like we require some detailed level of understanding as to how this is going to resolve from a policy perspective. We don't have any notion of actually maintaining a transaction, and we never get anything back that says, yeah, what I sent down has actually been realized in the FIB or in the RIB or in the FIB. And then from using that device or vendor-specific SDK perspective, I think vendors love to have customers using their SDKs. The problem is you send us something that is for JET. We're not going to do anything interesting with it from an Arista perspective, and vice versa. So this is not portable, and it's it's very pairwise integration oriented. So with respect to gRIBI, there's two parts to this. There's an actual service to inject routes into the routing table, and then we also have a query mechanism. From the device's perspective, the control plane, like we're letting the control plane, as we've interacted with the device and the control plane and routing protocols, to date, they do their thing. IGP resolves just as an IGP has always resolved. BGP is doing its own thing. But we can now start to do some interesting things by defining specific next top groups, and we can do kind of surgical overlays inside of the device's routing stack. And we can still rely on things like ARP, neighbor discovery, to handle the low-level details of how does that packet get encapsulated to the next top. Or if we're doing something with MPLS, we can actually impose a label stack and let the device kind of figure out the hard parts that in the OpenFlow or the P4 runtime domain, we'd actually have to maintain and do all ourselves. This is a pretty common model here. I think this is how EOS renders the RIB. This is pretty common across implementations. You have BGP processes, ISIS processes, static routing processes. All of this gets into some sort of RIB resolution manager. These populate the LFIB or the IP fib respectively, and that gets shoved into hardware. In this case, gRIBI represents itself as a server or a protocol itself. It can have its own administrative weight, and we have something that's sitting outside off box that's capable of injecting routes into the device. This is subject to the standard routing resolution behaviors that you have inside the device as well. So what do we use for representing the routes and the constructs associated with routes? Well, gRIBI leverages OpenConfig, and specifically it leverages the abstract forwarding table model inside of OpenConfig. Now the AFT, I might refer to it as the AFT, is kind of an interesting beast. We can have next top groups with next tops with weights comprising next top groups. We can actually have various tunnel types. So we can specify IP encap, GRE encap, GUI encap. We can specify label stacks. There's quite a bit of flexibility inside of the AFT itself. Additionally, because we're using a modern RPC mechanism, we can actually start to do some interesting things here. So every time we program or send an entry into the RIB, we get an operation ID. And then when we query the device, we get an idea as to what action we took is actually responsible for populating the RIB with that particular entry. We can also get both RIB and FIB acts. So we can get some acknowledgement from the device that yes, this entry or this action that I took inside of the routing from a RIB perspective has been installed. We can also extend that, and we can get some actual validation that whatever that entry that we installed into the hardware is actually in the hardware. So this gives us a mechanism to say, if I ran out of hardware resources and I wasn't able to actually get a FIB ACK, I can do something intelligent from the perspective of the controller. Maybe I don't want to install this tunnel destination. Maybe I don't want to actually rebalance the traffic in this manner if I can't actually service that request from the perspective of the hardware. The other thing I get here is I get support for client or controller redundancy. I can operate in an active standby configuration. I can run in an active configuration. Because these are programmed into their own process, we can also have some notion of persistence. So if I disconnect from the device, those connections can, those routes or entries that I programmed into the RIB, can be persistent. If I have a process crash, we can have some notion of recovery. And the other thing that we get here is we can have some notion of transport security. So instead of using unvalidated BGP connections in order to inject something into this, I can use MTLS and SPIFFE so that I can, hey, Some clients are allowed to actually write entries into the RIB. Some are only actually able to kind of understand what has been programmed into the RIB from the perspective of the controller. So what are some example applications? Well, perhaps I have a scrubbing application where I want to surgically reroute traffic from that's destined to a particular endpoint to a scrubbing solution. I can inject a /32 into the device, divert this traffic into a tunnel, and I can run it through a complex and then re-inject it back into the network downstream somewhere. I can also create label stacks, which allow me to send traffic across a variety of different traffic engineered paths. And it need not necessarily be MPLS label stack. It could be a combination of IP tunnels, gRPC tunnels. A variety of different forwarding constructs can be applied here. The other thing that we want to keep in mind here is that this is actually route injection. We're not actually configuring. We're not creating persistent config. So we're not going in and creating an interface tunnel or creating static next hop groups which are defined inside the configuration and actually committed to configuration. We are creating these kind of ephemeral routing entries which are can be programmed at a much higher rate than the standard config pipeline might allow itself. So this is just a slight visualization of what's going on from a scrubbing perspective. Here I have traffic that is the orange traffic is effectively the garbage traffic that I want to remove in the scrubber. I have a device here that's going to divert this. This looks like effectively three things here. On the lower right-hand section, I am creating the IP tunnel. This has a source IP of 111.111 and a destination of all twos. I have created a next hop group here which points at this particular tunnel destination with a weight of 1, so all traffic is associated with this. And then I'm specifying a route entry that will surgically grab 100, 100, 101 /32 and send that directly into that tunnel. From a label perspective, we can create label stacks. This looks a lot like what you would do with BGP SRTE or static segment routing traffic engineered tunnels. We can create multiple label stacks with any combination of labels. In this example, we're pushing labels 201 and 300. Top label, the top label is 300 here. We're just showing a handful of the examples here. We can also specify alternate weights with these. So next hop AFT here, ID 1000, is actually going into a next hop group where I have 3 label stacks with individual weights of 1, 2, and 5. Traffic will be load balanced accordingly with these label stacks. Now, could I do this with BGP SRTE or even something like PSEP? Yes, I could, but I can now take advantage of a modern programmatic mechanism in order to facilitate this. So now I'm going to spend just a little bit of time talking about the RPCs and what goes into these. So there's effectively 3 interesting RPCs. We're never actually configuring something inside of the OpenConfig AFT model. What we're doing is we're modifying things. So we have the modify RPC, which is used for injecting the entries. This is also used for negotiating various connection parameters associated with whether or not I'm going to be the active controller or not, as well as a get RPC. This allows us to get the last agreed upon programmed entries that were pushed into the gRPC agent from the controller. And then we have the flush, which is a mechanism for us to basically blow out all of the entries that we might have inside of the given VRF or across all VRFs for gRPC routes. This is only to be applied to gRPC routes. So this is all defined using protobufs. These are standard gRPC and protobuf messages. The modify RPC is going to return a modify response. Each modify request operation, which is what we're actually sending to the routing device, contains an ID, a network instance or a VRF, Network instances are what OpenConfig refers to as VRFs. It specifies the operation that we're going to apply, whether we're adding, whether we're replacing, or deleting an entry, and then it has the details associated with the entry itself. The response, which is what the router sends back to the controller, or the programming entity, sends back the ID, the status of its RIB, whether it was RIB or FIBACT, and it includes a timestamp. When it comes to the modify RPC, or the modify message, I should say, we have a couple of session parameters. We can specify the redundancy model for the connection that we're establishing to the device. We can specify whether or not we expect this to be a persistent in the gRIBI routing tables, or it can be deleted. And we're going to specify the type of ACK that we can support. So we can either support RIBACK or we can support RIB and FIBACK. The modify message also includes an election ID. This is used to determine what is your primary or your active controller or client. It always, when a client connects, it sends its election ID. The device responds with its highest election ID, the highest election ID that it knows about, and then each AFT operation or programming action that we're going to take has the election ID, and the gRIBI server is only going to, and by server I mean the gRIBI process inside of the router is only going to process the operations from the client with the highest election ID. Get has a separate response. This allows us to interrogate the device to find out about the gRIBI programmed elements that it knows about. So we can request all of the gRIBI AFT programming entries that we have, or we can choose to filter those based on VRF or based on the AFT type that we're interested in. And if you have negotiated some form of ACK, you're going to get back the entries that correspond to the last acknowledged, the last confirmed acknowledged entries as programmed. The flush, this is when things go sideways, or you really want to close things out. You don't need to have those entries in anymore. The flush request is a request to flush all the entries associated with a VRF or across all of the VRFs. And that's going to give you the result and the timestamp. This is really to be used in case of controller malfunction. If you're doing this in a controlled manner, you would also be able to just send gRIBI modify request with a delete action. So now let's step through an example. In the upper right-hand corner here, I have a device. We're going to look at traffic destined to 111. Traffic destined to 111. We're going to send that. Our intention here is to do weighted load balancing across some of the links here in this device. The links are going to use a resolved next hop, which is injected from a static route. So we're going to resolve everything destined for 111 out 192.168.1.1. And as it stands, we have routes for this across Ethernet interfaces 2, 4, 5, and 6. So as we mentioned before, we establish a connection to the gRIBI server. We have an election ID. We're at 1. We're going to create our next hops. Our next hops have to be created individually. So in this example here, we have ID 3 and 4, which are responsible for creating the next hops that specify the next hop of 192.168.1.1 and an interface of Ethernet 5 and an Ethernet 2, respectively. Next, we'll create the next hop group. We'll take those indices, 2 and 3 and 4. We'll associate weights with those next hops, and we'll create a next hop group, which is going to be used in order to specify the route. So the next hop group contains the references to the next hops. We now add our value in here of 1 and 3 respectively. And then we add the route for 111/32 pointing out to next hop group with a value of 2, ID 2. What does this look like inside of the routing table? I've shrunk the text here a little bit here. You can see that we're interacting with everything inside of the global VRF. you can see that we have we have actually programmed in here for resolving 192.168.1.1/32 is statically configured across all 4 Ethernet interfaces. But if you look at the entry specifically for 111/32, you'll see that we have the respective weights applied here of 3 and 1 for the interfaces that are associated with it. If we didn't do this, we would just see the resolution associated with this of ECMPing across 2, 4, 5, and 6 rather, and there would be no mechanism in order to be able to apply balanced forwarding. What I didn't include and what the 3 dots were indicating was we had also programmed in here. You'll see the G percent symbols indicate that these are gRIBI programmed routes. Is the corresponding entries for 222. So we also in that same update request introduced routes for 222, which did effectively the same balancing but across different interfaces. This is just to keep the example brief. I've included some references here. The gRIBI reference and the specification is on a GitHub repository under the OpenConfig umbrella. There's a document in there that outlines some of the motivations behind doing this. The spec is there, the protobufs are there, and there's also a gRIBI Go reference implementation. From a conclusion perspective, I think we've had customers asking us for surgical routing or programmatic routing interfaces for quite some time, and gRIBI really provides the first real open mechanism for programming, and I mean legitimately programming RIB state into a device without using interesting routing hacks. It does support a wide range of forwarding paradigms here, a wide range of tunnel end caps. You can even manipulate policy routing to some extent with this. It is not constrained to your classic traffic engineering technologies of RSVP with PSEP or segment routing with BGP coupling or PSEP coupling. And I will point out that there are multiple implementations of this. I know that there's an implementation from Juniper. I do not know what the status is of implementations from other vendors, but I think from a practical perspective here, we are reaching a point where operators can start to utilize modern programming techniques in order to interact with the devices and to program routing state. We'd encourage you to take a look at what's available out there, harass your vendor of choice, start kicking the tires with this. It does provide some interesting new capabilities. And with that, I am done. Are there any questions?
Hello, I'm Kemal Shanta with Thousand Eyes. So thanks for the presentation. It really offers a lot of advanced traffic engineering capabilities, especially as you mentioned for DDoS or, for example, moving piece of traffic based on the net flow information to different router with the same peering within the same POP, right? That would be the straight away. Now you mentioned that one of the things is that there's some effort to standardize this as part of IETF. No, okay.
No, this is not an IETF project, or this is not work that is currently within a working group at IETF that I'm aware of. I2RS was a working group in about 2016, 2017-ish timeframe. There were a couple of RFCs, informational largely, and a few Yang models that were published. It did not interface with what I would call kind of modern programming mechanisms. Yeah. And I think what you are seeing in we have a few things kind of coming together here from an interesting technology perspective that enable this. We have a reasonably vendor neutral representation of a device's FIB. We have a model that complements that, so that you can get information out of the device from a telemetry perspective, and you can actually now program it in an interesting perspective. This provides a mechanism for you to to program it. It is an OpenConfig project, so if you have questions or if you have comments, you want to kick the tires on the code and the reference implementation, it's all there.
So that's the next part of my question, essentially. So beside Juniper, who you mentioned that have like some sort of implementation in Arista, what is the minimum set of requirements for any kind of vendor to start working with this?
I think a vendor would need to have the ability to support the AFT device model and the ability to interact with that programmatically. Most implementations have some form of ability to host daemons or extensions, and it would likely be up to the vendor in order to implement this service such that they can manipulate the internal state of the routing table. Like if you want to be able to do things like RIBAC and FIBAC, you need to have a deep understanding of what your hardware is capable of, and you need to be able to understand how this is going to resolve inside of whatever your respective RIB form is.
Got it. Thank you so much.
Yep.
Hello, I'm James Schenk from Team Cymru, but I'm asking a question on behalf of Blake Willis from Zio. He's wondering, what have you seen in terms of scale and performance on various boxes for this? And an example of what he's wanting to know about is how many routes would you be comfortable pushing at one time into various gear with this?
So it's kind of an interesting question. So there's two parts to this. One is the construction of the next top entries, the next top groups. If those already exist and you've created those structures, like the actual programming of route entries is very fast. If you need to create tunnels and you need to kind of create the corresponding like those first constructs that I was referring to, like if I'm doing like gRE tunnels or GUI tunnels or label stacks, like the programming times for those are going to vary based on implementation. But we've seen tens of thousands of prefixes programmed in single-digit seconds.
Thank you.
Are there any online questions? I appreciate your time. Thank you.